Good afternoon. So today we will continue our discussion on using conservation of momentum to solve more problems. So as we said previously, if your momentum transfer is zero, then your P final minus P initial will be zero if you have no external force, right? So most of the time we're using PI equals PF to solve our problem. So the momentum remain constant. So there are two different ways where the transfer could be zero. One is simply there is no external force. Net force is zero. So sometimes we do this by either making a system, some of the force become part of your system, internal force, or sometimes we ignore friction, right? So we can make there's no external force. Sometimes we can make this momentum transfer be zero, even if there is external force. We can still make the transfer go to zero when time is small, when t is really small. So when f dt, when t is really small, this is approximately zero, we can still use zero on the right-hand side, okay? So that is called the impulse approximation. So for example, here, let's look at another question. This is an example of we can use impulse approximation. So the problem is like this. You have a bullet and you have this block of gel. So that when the bullet gets shot into the gel, it got embedded in the gel. So you can see if this is a collision between two objects, the bullet and the gel, it is a perfectly inelastic collision problem, right? Because after the collision, they stuck together. So that's perfectly inelastic. Okay, so once the bullet is embedded, the bullet and gel entire system is going to slide on the floor for some distance. So you can see that during the collision, there is still the friction acting on the bullet and the gel, right, on the gel. But because the collision happened so fast, we can ignore the impulse from the external force and still are able to use P initial equals P final. Okay, so you can see this is very similar to a previous problem we did in our last lecture. And we can break it down into two sequential problems. First problem is perfectly inelastic collision between bullet and the gel. And the second is a conservation energy problem for the sliding part. Okay, so it's telling me how far it slides, and it's asking what is the initial speed of the bullet. Okay, so I'll give you a little bit of time to think about this question. You can draw a picture and try to solve for the initial speed, or you can at least apply conservation momentum to the first section, the collision part, and see how far you can get. All right, I'll give you a minute or two to try to set things up yourself. All right, so I'm choosing my system to be the bullet plus gel. And I wish to use conservation of momentum to look at the collision process, okay? Then I need to equate P initial, momentum initial equal to momentum final, okay? So anybody can tell us, what do we define to be the initial moment? So what is our initial moment? So we're saying we want to look at the momentum initial. So when is initial?
Before the bullet hits the gel.
Yes, very good. We will say just before the collision happens, just before the bullet hits the gel. Very good. And final moment?
When it stops due to friction.
Ah, very good. I do wanted to, let's think about that for a second. The final moment of the problem is indeed the collision happened, they slide and then they stop. The final moment is they both slide and they stopped. So here is when they stopped, right? So here. Do you want to use this moment to be the final moment that you will use conservation of momentum on?
You wouldn't want to use it as the final momentum because there would be the external force of friction that you'd have to consider.
Yes, very good. So from here to here, you can see that is the a process where you cannot ignore the effect of the external force. In fact, the external force does have the impulse that change the momentum of the system. Here, we are only applying this only to the collision, okay? And the second part of the problem is the sliding, it's not the collision part. First part is collision, and after collision, you have sliding. So we're only gonna do the collision part, and we're gonna do the sliding part later, okay? So this is very important that the final moment is, so that's why we don't say after collision, we say right after, because after you can say, oh, when they are both stopped, that's after collision. But that is when they already started sliding. I want to see the moment when the collision just happened and they haven't even started sliding yet. So I say right after the bullet hits the gel. Right before and right after. Okay, sometimes you can say a long time before if the velocity doesn't change, so it doesn't matter. But right, if the velocity, sometimes the velocity may even change. So you need the moment it hits the gel. You need the moment right before it hits the gel to be your initial moment. Okay, I got a question from Eric. Is final when the bullet collides, but before the gel block moves? Yeah, so final is right after the bullet collides, but before the gel started moving, and happens so fast. The collision happened really fast. But even though it happens so fast, we still separate that very fast process into initial, starting point, and the final. Okay, so we need to put Pi equals Pf. So Pi initial would be the momentum of the bullet initial. Bullet has some initial momentum, and the gel has some initial momentum. And the bullet and the gel together have some final momentum. They're together, right? Final. So the gel is stopped at the beginning, so no initial momentum from the gel. So it's really just the momentum from the bullet, right? Momentum is mass times velocity, so that you can see the left-hand side becomes m bullet, velocity of the bullet, equal to gel and bullet together after the collision. So they're together, right? So you use the total mass, so they have the same final velocity. That's why you use both the masses times velocity of the gel, which is both the bullet and gel together right after collision. So you can express the velocity of the bullet using the rest of the variables, the mass and the velocity of the gel. You can see that here we want to solve for a V bullet, okay? We don't know this quantity, But if we can know how fast they're moving right after collision, we can plug it in and solve for the velocity of the bullet that it started with. And so that goes to the second part of the problem. The second part of the problem is a sliding part. So you can see the final moment here becomes the starting point of the second section, right? So so right now is starting, finish, and here from start, finish. So my final moment is right after the bullet hits the gel, is becoming the starting point of the second problem. And I will use conservation of energy to solve that problem. Okay, so to use conservation of energy, again, I need to identify my system. Since my system is still bullet and gel, my system remain the same. Okay, so it's the same system as before. And I need to identify a initial and final moment. Okay, so again, let's add these. So the initial moment for the second part, for the sliding part, is right after the collision. But they have not yet started sliding. They haven't started sliding it. And the final moment of the second part of the problem. So what do I choose for the final moment for the sliding part? What is my final moment?
When it stops sliding.
When it stops, very good. So when it finally stops. When they stop. Okay. All right, so finally you can see the final moment has 0 energy, right? You don't have to think about potential energy because they're moving on a horizontal surface, 0 kinetic energy, so total energy of the system is 0. To start with, they really just a bullet and gel together are moving with the same velocity, so they have this kinetic energy. That's why I put 1/2 mv squared in initial energy. No input, okay, again, there's nothing that is speeding them up or pushing them, right? So there's no input. There is an output because friction is now an external force acting on the system. So this friction transferred energy of the system. So, and then the work done by friction is negative friction times distance, force times displacement. Okay. Friction, you know, is mu times n, mu, the coefficient times normal force, and normal force is the mass times gravity, so mg. Okay, so putting everything together, you can see I get 1/2 mv squared. This is the mass for both, right? Mass total. This is also the mass total for both bullet and gel. You can calculate. It already tell you how far they slide. This is already known. So I can solve for velocity of the gel, which is 2 meters per second. So once I get the velocity of the gel, I can plug it back in here and find how fast was the bullet shot into the gel. You go back to do the first part, right? Simply just plugging in this and you get 400 meters per second. Okay, so this really last step is you just plug in the V gel back into your previous equation. You can see this is very similar to the problem we did this past Tuesday. Is we were given 2 blocks, right? One shot into another and they stick and they slide. So we given this velocity, we find the distance. This is a sort of a reverse process. We give your distance and we want you to find the velocity. But you can see essentially they're the same type of problem. You have a collision and then a sliding. You have 2 sequential problems and 3 instant. Those 3 instants are instant 1 before collision, instant 2 right after collision, instant 3 when they stop. Right? You put instant 1 and 2 together, and that is your initial final moment for the conservation momentum problem. You put 2 and 3 together, that's your initial and final moment for the conservation of energy problem. Right? You separated this process into separate this entire process into 2 different sequential processes. Okay, so that's another example that you have seen that's very similar to something we have already done. Okay, so following up, there are a couple of checkpoint questions you've done. I would like to go through them one by one. the first checkpoint question is, there is an external force F, constant force, applied for a total time t, delta t on the block that was originally at rest. There's no other external force, then there's no friction, right? Just this one. And the block will eventually have a final velocity v. Suppose you repeat the experiment with twice the mass using a force that's half as long, then how long do you need to apply this force? So this is a direct application of conservation of momentum, or you can call it the impulse momentum theorem. Is the P final minus P initial. There is a change in the momentum of the system. That change is done by the impulse, right? So here we do have an impulse, right? Okay, so when you have a force F applied for time t, you manage to increase the block's velocity from originally 0 to a velocity of v. So you can see mv is equal to F times t. This is what the first sentence is telling me, right? Now, it's asking me, how long would I need to apply the force? Only half as big, so half as big. For how long? Different time, delta t prime, to a block with twice the mass, twice amount of the mass, to the same velocity, v. Okay. Force is half now, mass is double. So you can see delta t is going to be 4 times, delta t prime is going to be 4 times delta t. You need 4 times as long in order to achieve the same effect, right? So A is correct, okay? It's a direct application of your momentum impulse theorem, or you can call it conservation momentum. It doesn't, it's not just the same, okay? Second question called bouncing ball. You have case 1 and 2, they're exactly same except how in case 2, you can imagine this is sort of like a cushion, right? When the ball bounces on it, it kind of dip down and then coming back up. This one does not dip down. This one directly going back up. Okay, this is more like this is like a cement. This is more stretchy rubber. So in which case the average force is bigger. So what do you guys think? Which case the force is bigger?
Case 1.
Case 1 is bigger, and why is that?
Because the ball is bouncing straight back. The cement floor is absorbing all the momentum.
Right, case 1 with the cement is like you can say there's no give, right? It's like what we say there's no chromosomes, like no chromosomes for a car. So you have bouncing the ball back to you can see exactly same momentum, right? And same momentum initial. So you want to change the momentum the same, but in case 1, you only have a short amount of time to do this, to apply this force. So this force has to be bigger, right? In order for you to have the same change. But in case 2, you have a longer time. T is longer because you get a longer give. So this force doesn't have to be as big, right? Force is smaller. Very good. So case 1 is going to be experiencing bigger average force. Third checkpoint question. Okay, so I have 2 blocks. So you can see at before and after collision moment identified. Before collision, this green one is moving velocity v. This one is at rest. After collision, this one bounces back. This one moves forward. Okay, so was the collision elastic? So I know that this is a frictionless floor. Again, I can use conservation of momentum to do P final equals P initial. Initial equals P final. And initially, what you've got? You have got 1m. I'm going to call this little m, this big M. Okay. So initially, you get just mv because this one is at rest. Okay, so it's 0 momentum. So just the momentum for for the little m. So my system is m and m, two m's, right, together. And finally, this one bounces back. So how do I write the momentum for little m after collision? Mass time velocity v over 3. How do I account the flip direction? Let's call this positive. So this velocity in the opposite direction. So how should I write it in my equation?
Put a negative sign in front of it.
Yes, yes, very good. So I put a negative sign in front of this, and this one is in the moving forward. So it's going to be positive v over 3. Okay, so from this, I know that, okay, I know if I move this and this together, I get 4mv over 3 is equal to capital MV over 3. So you get the one of the blocks is 4 times the mass of the other. So that is information we can gather from what's given, okay? This one is 4 times the mass of the other. It's asking, but it's not what it's asking. It's asking, was the collision elastic? So do you still remember what is the definition for an elastic collision?
Momentum is conserved.
Momentum is conserved for elastic collision. Yes, momentum is also conserved for inelastic collision. So, but there is one more condition for elastic.
The kinetic energy is conserved.
Yes, kinetic energy is a constant before and after collision. Very good. There is no kinetic energy loss during the collision process. Okay. All right, before I do this, I got a question in the chat. So let's look at this together. Confused on this, how would the movement of the right block after the collision be v over 3 and less than velocity before collision if it was stationary before the collision? So we talked about generally when you have a smaller object hits a bigger object, right? Then the smaller object will bounce back and the big object will be moving forward. And you can see the big object has to have a velocity pretty much smaller than the v. Otherwise, because all you get, the momentum of the system is little m times v to begin with, right? So it's now being shared by the little m and the big M. So however they're going to split this velocity is going to depend on the mass. In this case, the red block is exactly 4 times of the mass of a little block, and conservation momentum tells us that if you have one move bounces back with v over 3, then the other one will move forward with v over 3. All right, so the kinetic energy has to be the same. So let's see if it is the same. So before collision, you have the kinetic energy of this block, which is 1/2 mv squared. This guy has no kinetic energy, so that's just your final. Whether that equals the final is again 1/2 mv over 3 squared. Again, the kinetic energy, the fact is going backward doesn't matter, right? It's because the velocity is squared, and this guy is 1/2 times 4 times of the mass moving with 1/2 v over 3 squared. Okay, and this is going to be uh, 5 over 18 mv squared if you combine everything. And you can see that it's obviously not the same as 1/2 mv squared. So it's not elastic, right? Not elastic. Okay. All right. Now we got one more question here. You can see it's again, I would call this the same problem as the bullet problem, even though it looks very different. Okay, so what is this problem we're looking at? You have a projectile and it's shot to a pendulum, and once they collide, they stick together, right? They stick together, or maybe this sometimes is embedded in there, but in this case they're just stick together. And again, that's a perfectly inelastic collision. So right after they stick together, this whole thing will swing up, right? This whole thing has been shot up. So it's going to swing up and go as high as height h. So given this height h, what is the velocity of the projectile when you first fire it, or when it just before it hits the pendulum? So I say again, hopefully you see this as well. It's the same problem as before. This is a ballistic pendulum, the same as the bullet and gel problem, right? First, the bullet and gel is you have a collision, and then they slide. In this case, you have a collision and then they swing up. So whether it's sliding down to a stop or if they are swinging up to a stop, it's really physically no difference. In terms of the physics principle you apply, it's the same type of problem. Okay. So why don't you guys take some moment and try to tackle this problem on your own? I'll give you a couple minutes to discuss within a breakout room. And afterwards, I'm gonna ask how far you've got, okay? So go ahead and give you a few minutes in the breakout rooms. All right, so everybody came back. I would like to ask, anybody would like to share with us, what do you think our general approach to solve this problem? What is the general approach to solve this problem? Usually, if we can articulate the general approach, we have a pretty idea of what to do.
We set the momentum of the system, the initial momentum equal to the final momentum.
Okay, so you're using conservation of momentum for the collision part, right? Okay. So will that be enough to solve for the initial speed? If I do that, conservation of momentum for the collision problem applied on the system of, so I'm going to identify my system first, little m and big M. Okay, yes, very good. I see a collision. I'm going to use conservation momentum to see how far that is going to get us. The initial momentum, this one is at rest, this one is moving, so it's really just going to be mv. Final, what is the final momentum of the system? Now the question is, what is your initial and final moment? Your initial moment, I would say right before M hits big M. What is your final moment? Anybody would like to say, tell us, what do you think the final moment would be?
Right after little m hits big M.
Yes, right after little m hits big M. Excellent. So here, the final moment, very important. You cannot use when they stop, right? It's like that's the second part of the process. Your collision part happens very fast. It's right before collision and right after collision. So this is your final moment. Okay, so my final, when they are moving together, they stick together and they will have some kind of final speed. Once this embedded in here, you can imagine they start swaying up with this velocity, V final. Okay, so what do I need to solve? I need to solve for V. So if I want to solve for V, I need to know V final. But I don't know V final right now, right? So you can do the momentum and you can see, okay, I need more equations. I need some more information. So what do we do to find V final? Conservation of energy, as John was saying, very good. You see, the second part of the problem is a conservation of energy problem. So for this problem, you have again two moments. The beginning of the swing process is that right after they hit, because right after they hit, they're going to swing up, right? So that's your initial moment. And your final moment is when the M swing up to the maximum height H. So I'll get back to your question, Eric. Is that final the same as when the large object reaches height H? Yes, so when large object reach height H is as high as they can both go. That's also when they are stopped, right? Because as high as you go implies you're not going any higher, so you must stop at that moment. The second part of the problem is conservation of energy. All right, so the conservation of energy part, the initial energy, final energy minus initial equals E in minus E out. Okay, so for the energy problem, I do want to, you can see you have a height. Whenever there's a change in height, I want to include potential energy. So I'm going to say M and little m and big M and the Earth are going to be my system for the energy part. Okay, so you can see that final energy is going to be they stopped so no kinetic. They're at a height above, so they're gonna be some potential energy, right? So finally, what's gonna be M plus big M into H at a height H, that's your gravitational potential energy. Initially is they started moving with this velocity, so kinetic energy for both of them, right? They're moving together. And there's no input, there's no output, okay? Is equal to 0. And then you might wonder, okay, is it true that there is no output? Is there any external forces on it? Well, I know I shouldn't be thinking about gravitational force because I have included Earth in my system. So gravity is now an internal force. Another force I could have is tension, okay? But you know that for pendulum, we have done this before. Your tension doesn't do any work. Your tension is always perpendicular to your trajectory, to your path, right? So your tension doesn't do any work. See, this is your trajectory, right? This is your change of your little change of velocity. Velocity is tangential, right? So your little change of your displacement is in that direction. It's perpendicular to your force. Okay, so you can see there is no external. There's no external work. There's no energy output. So you can see we can find our V final is simply going to be square root of 2gh, and you can plug it back in here. Okay, so you found your V final, and we use V final. Yeah. And you can plug it in and find your initial velocity of the bullet or of the little end. Okay, so we have done these type of problems 3 times. Okay, it's the hit and slide, collision and slide, or collision and the swing up. It's all the same process. You can see it's very similar, and all these 3 problems are a perfectly inelastic collision. Okay. Sometimes there are problems of elastic as well. So for example, you have probably see this on your pre-lecture. This is an elastic problem. I'm going to actually save this problem to the end. And we are going to discuss the conservation momentum in 2 dimensions first before we do this problem. All right, so far you have already seen how do we apply conservation momentum. Sometimes collision happens in 2 different directions, not just in 1 direction, okay? And but the process is exactly the same. You can break down momentum still remain constant, right? Because it's a vector in 2 dimensions, just like how they were in 1 dimension. You can do this by breaking it down into x and y component. So you can write down the conservation momentum in your x component, and you can write it down in the y component. Okay, so what does this look like? So when you write it down into the component, your vector sign, you can lose your vector sign. So the velocity in the x component, simply add a little component here, velocity in b as a component, and velocity final x component and component x for the b, right? You can do the same thing for the y component. So no matter if it's 2D problem or 3D even, you can just simply apply this equation over and over again in each of the directions, each of the dimensions. Okay. Now, when it's 1D, so when it's 1D, if this is VA going this way, right? Initial is going this way. And let's call it V naught. And I've defined this as a positive direction. And if VA is going this way as your final, right? So it's the same magnitude final. How we take care of this in 1 dimension is simply, okay, MA V naught initial plus MB VB initial equals MA VA final. This VA final is flipped directions. We're simply going to add a negative sign. We say negative MA V naught, right? So the vector sign becomes a negative sign when you do 1D. When it's 2D, is exactly the same. You look at, so for example, if this is my VA initial, right? And if this is your VA final, you look at the X component, and you look at the X component, if it's flip direction, you add a negative sign. Okay, and everything else stayed the same. So let's use some concrete problems to see this. Here we have a question. You have two objects, A hits B. It's a 2D collision. The initial momentum of the ball A is indicated by this arrow right here. Okay. And the final momentum of the ball B is indicated by this arrow here. Okay. So from these information, can we figure out what should the final momentum of the ball A should be? Given that so momentum initial should equal to momentum final. So initial, you have PA initial, PB initial. You have PA final, PB final. It's for A and B system. Okay. B originally is at rest, so it's really just these. Okay. You can look at them as if they were vectors, or you can break them down into component, X component and Y component. You write it down for the X component, you're going to have this. So whatever component you have in the X direction, you should have the same amount of component finally. So initial equals final. Okay, so I'll give you a little bit time to discuss and see which choice did you want to choose. All right, so let's go for 10 more seconds. If you haven't voted, please do so. All right, any last minute vote? All right, so I'm going to go ahead and close this. This is our results. Okay, so we can see there's a slightly majority choosing for B than A. Okay. All right, so the convenience of breaking it down into components, we can just focus on the X component without worrying the Y, because the conservation momentum should apply in both X and Y direction, right? So let's look at what is in the X. The initial momentum of A in the X direction. So let's look at it. It's on the grid, so it's easy to see. So how many units is in the X direction? 2 units, right? So we can just write 2 here, equal to the AX final plus the BX final. So how much unit for the B is in the X direction? You can see that it's convenient to look at it in the grid because you can tell it's 1 unit in the X, right? So this is 1. So that tells you PAX final has to have 1 unit in the X direction. So looking at these vectors, which one gives you a 1 unit in the X direction? How many units does this one give in the X direction?
Three units.
Yes, so not A, right? That's 3 units. B does give me 1 unit in the X direction. C gives me how much unit in X direction?
-1 units.
Yeah, -1. Again, you have to take account into the direction when you put it into components, X direction. D has 0 units in the X, right? So looking at all of these, it has to be B. Okay, so B is correct. All right, so now let's solve a problem together. It's a 2D collision problem. So you have an object 3M moving along X direction. When it hits, and then it breaks out into 2 pieces. So things like this could be like break of an atom. All right, I don't know why I got locked out, and then it locked back me in. Sorry, we got disconnected for a little while there. Okay, so hopefully you're still with me. Particle collisions, like I said earlier, you can, things like this, 1 atom splits into 2. So here we have a 1 3M splits into a 2M and 1M, but they're now moving in different directions, okay? So it tells me the angle of theta 1, theta 2, and asking what is V1, now what is this one? And also what is V2? Okay, so let's solve for this question together. So once you have velocity in in the 2D, you will break it down into 2 different directions, okay? So let's call this Y and X, and this is V2, make an angle theta 2, okay? So you have, this is V2X, Y direction V2Y. So V2X is V2 times what? Cosine theta 2. V2Y is V2 times sine theta 2, right? Okay, so apply the conservation of momentum in both X and Y directions. In the X direction, P initial X equals P final X. So you can see initially, this is entirely in X direction. So initial momentum is just 3M times V